Hello, my name is Nick Huntington Klein. In this video, I'm going to be talking about game theory. I'm going to be talking about what a Nash equilibrium is, what a best response is, and also how to find the Nash equilibrium in a simultaneous game, on a game table. So first of all, what is game theory? Game theory is the way that economists think about strategic interaction. So when we are talking about, most of the time we've been talking about thinking, we're going to buy this thing, we're going to sell this thing. That's a decision that we make on our own. And the actions of other people affect us, certainly. If somebody buys a whole bunch of stuff or sells a whole bunch of stuff or enters a market, that affects us. But if the payout that we get specifically is based on the combination of what I do and what somebody else does, that's going to be a strategic interaction. I might think about, how am I going to react to what you do? How are you going to react to what I do? How should I act in anticipation of what you are going to do? And that is game theory. When we have a game like this, we can think about, we have the players that are going to play the game, and they're going to each take actions in the game. And based on the combination of those actions, we are going to have some sort of payoff or payout. And I'm going to be choosing my actions while thinking about what you might choose in such a way that gets me the best result possible, and you're going to do the same. This can lead us to a Nash equilibrium. What a Nash equilibrium is, it is the typical prediction that we would make for a game. What is the outcome of a game going to be? What are people going to do in the game that's going to lead us to this outcome? And so what it is a Nash equilibrium occurs when neither player wants to change their strategy by themselves. Okay, so if we have two people and they're both playing a game, and then they play the game, and then they see what they did. They see whatever the outcome of the game was. If one of them says, man, based on what you did, I wish that I had done something else, then it's not a Nash equilibrium. Okay? That's a good sort of a trick for testing if something is a Nash equilibrium. Think about what people have done, look at the outcome, and then think, assuming that you stayed where you are, do I want to change what I did? So let's take rock, paper, scissors as an example. Rock, paper, scissors, at least in its, it does not have a Nash equilibrium, at least in what's called pure form. It does have one in what's called mixed strategies, but we're not going to cover that. But rock, paper, scissors. So you play the game, this guy goes rock, this person goes paper, and then paper covers rock and they win. Okay, so is this a Nash equilibrium? No, it's not, right? Because this rock person over here is losing. If they would do better. They think, man, based on the fact that you played paper, I wish that I had played scissors. Of course, then based on the fact that they played scissors, they would rather play rock. Based on the fact that they played rock, they would want to play paper, right? So there's not a Nash equilibrium there, because no matter what people do, they're always going to wish that they'd done something else based on what the other person did. Compare this to a game called matching pennies. So in matching pennies, what you do is I pick heads or tails, and you pick heads or tails. And if we both pick the same thing, if we both pick heads or we both pick tails, then we each win $1. And if we mismatch, then we both lose $1. So let's say that I pick heads and you pick heads. Okay, well, based on the fact that I picked heads, do you want to change what you did? No, right? You want to keep picking heads. If you pick heads, do I want to change what I did? No, I want to keep picking heads as well. So that would be a Nash equilibrium, because based on what the other person did and what we did, we don't want to change our behavior. We can think about this through the concept of best responses. A best response is, given whatever thing that it is that you are doing, what is the thing that I could do that would give me the best payout? Okay, so in rock, paper, scissors, if you play rock, my best response is to play paper. If I play paper, your best response is to play scissors. If you play scissors, my best response is to play rock. Whatever the other person is doing, what I would like to do in response to that is my best response. Okay? And a Nash equilibrium we can think of as when both players are playing best responses to each other at the exact same time. So in the matching pennies game, my best response to you playing heads is for me to also play heads. Your best response to me playing heads is for you to play heads, right? So I'm playing a best response to you when we both play heads. You're playing a best response to me when we both play heads. Therefore, we have reached a Nash equilibrium. We can use this concept of best responses to solve any game. If we can write down the game, if it has a finite number of options that you can choose, there's always going to be a Nash equilibrium. Some of them require the mixed strategies thing that I talked about before, so sometimes you might not find it in the very basic form that we're going to cover it, but don't worry about that. At least in my class, I'm not going to give you any problems where that's going to be the case. You're not going to have to solve rock, paper, scissors. So how can we find a Nash equilibrium in a simultaneous game? Now, simultaneous game is when both players are playing at the exact same time. So like rock, paper, scissors, right? They both make the choice at the exact same time without knowing what the other person has done. That's the key for a simultaneous game. Despite this, we're going to end up with a Nash equilibrium. And so let's see how we can figure that out. So we can draw out these games in what are called game tables, where we have player A on one side, we have player B on the other. One of them is choosing which row they're going to choose. So player A, this is a very basic generic game, can either play up or down. So the player A is over here. You can see that the options that player A has. Player B is up here. Player B can choose to go left or to go right. And then based on the combination of their actions, we can see the payouts that they get. So here, if it's up and left, player A plays up and player B plays left. Player A gets 3, player B gets 4. Okay, so the way in which we can find Nash Equilibria in this game is to look for where both players are playing best responses to each other at the same time. That's what a Nash Equilibrium is. So we just need to find the best responses. And the way we're going to do this is we're going to go step by step. We're going to say for each strategy that player A could play, what is player B's best response? For each strategy that player B could play, what is player A's best response? Once we found all the best responses, we can know where they'd both be playing best responses to each other at the same time. So let's go step number 1. We're going to go row by row. We're going to go through each strategy that player A could play, and we're going to pick the column that is best for player B. So given what player A is going to do, if we imagine that we know what player A is going to do, how would B want to respond if they could? So first, let's imagine that player A is going to go up. So we're in this row for certain. Let's imagine that we know for certain that player A is going to go up. How does player B want to respond? Well, player B can either go left and get a payout of 4. Just highlight the 4, please. There we go. Or they can go right and get a payout of 2. 4 is better than 2, and so if player A goes up, player B would want to go left. I'm going to go ahead and highlight this right here to indicate that that is player B's best response. Now notice, when I was making this calculation, I did not factor in player A's payouts at all. Player A would rather that player B go to the right? Because A would get 4 over here and A only gets 3 over here. But we don't care about that at all. We don't care about trying to punish the other player. We don't care about trying to help the other player. We don't care about trying to find the cell where the sum total of the payouts is highest. We don't care about that. We just care about picking the best response that is best for us. And this is player B's decision to make. So player B is going to choose the option that gives player B the best payout, which is right here. Okay, so now let's imagine that player A plays down. If we knew for a fact that player A was going to play down, player B could go left and get 2, or could go right and get 3. 3 is better than 2, so we will highlight that right there. Okay, so now that we figured out what B's best responses are to everything that A could do, we want to figure out what A's best responses are to everything that B could do. So first, let's imagine that player B is going to go left. If we knew that player B was going to go left for certain, then we could ask, okay, what does player A want to do? Player A could go up and get 3, or could go down and get 5. 5 is better than 3, so we would highlight the 5 there. Now notice again, we did not care at all what player B's payouts were there. Because we held player B's constant. Player B said, yes, we're going to be in this left column. And it's player A's choice as to what row they end up in. So we're only going to look at player A's payouts there. And player A says, hey, if you're going to go left, I want to go down. Next, we can say, okay, let's say that we knew for a fact that player B was going to go right. Well, player A could go up and get 4, or down and get 4. Oh, now it's a tie. There can be more than one best response. So if there's a tie, either of these would give A the best payout. So we can highlight both of these. So if player B goes right, then player A would be equally happy going up or down. So now that we've highlighted all the best responses, we just say, okay, we're at whichever cell has both players playing a best response to each other at the same time, that is the Nash Equilibrium. And that is at the down right place right here. That's going to be our Nash Equilibrium outcome right there. Let's check it. A Nash Equilibrium is when neither player wants to change their own strategy, assuming that the other player stays still. So if player A is playing down, what does player B want to do? They could stick with what they have and get 3, or they could switch and get 2. 3 is better than 2, so player B does not want to change from this position. If player B is playing right, what does player A want to do? They could stick with what they have and get 4, or they could switch to up and get 4. That's the same either way, so they're happy sticking with down, and so A doesn't necessarily want to change their strategy, so A is playing a best response. Everyone is playing a best response at the same time. We have a Nash Equilibrium. Let's imagine that we did this wrong. We made a mistake. We somehow highlighted this up here as well, and we think that this is a Nash Equilibrium. Let's check whether that's true. Let's see how we can check our answer and try to show ourselves that it's wrong. We would follow the same steps. Does either player want to change their behavior? So first we would say, okay, well, let's say that player A is playing up. Does B want to change what they're doing? Well, if B sticks with left, they get 4. If they switch to right, they get 2. 4 is better than 2, so great, checks out. B is playing a best response. How about A? If player B is playing left, then player A can stick with up and get 3, or they can go down and get 5. Uh-oh. They could be better off by switching their behavior. And so they're not currently playing a best response here in up left. So that's not a best response. That's not a Nash equilibrium. All right, that's how you can solve out a game table, a simultaneous game in game theory to find a Nash equilibrium. Thank you.